make our calculations easier in the computer. And that was actually a pretty simple matter. It was just rearranging a few equations, the equation for the voltage divider and the equation for the ADC value. But basically what we ended up doing was we kind of harnessed the fact that the sensor was linear, and so we just solved for the value of the sensor, and that's what we did all our processing with. And those are just the formulas. And another thing we had to figure out was, how does a finger move? So I did a little studying on it and some measurements. Basically, I broke the finger down into 3 joints, because that's how many are in a finger. For my purposes, I call them the bottom, middle, and top joints. And what I learned and what I observed, as it turns out, is that these 2 joints move independently. You can move them on their own. You can control them on their own. But the top joint, the finger, does not. It moves as a function of the middle joint. And I had to figure out what that function was. It turns out it's different for each finger. And this is an example. This is the actual data. And again, as you can tell, it's pretty close to linear. So again, we decided to treat it as such in our software. So basically, I deduced an equation, a linear equation for each finger. I just used my fingers, and so it's probably varies a little bit from person to person, but that's how we did that. All right. So when it came time to actually start building the hardware, it was pretty simple hardware, but we decided we wanted to make it compact and look nice. So we decided to make our own circuit for it. Actually, let me start with the sensors. Let me back up. So the sensors are, this service right here is conductive, and we were sewing them inside cloth on a glove, and I was worried about noise and static. So what I decided to do was I got heat shrink tubing and insulated the sensor, which was nice because it allowed it to bend pretty freely still, but it shielded it from stray signals. And then, okay, when it came time to make the circuit board, we etched it. I designed it in a piece of software called Fritzing, which is open source and pretty easy to use. I made a layout, and then we etched it using the toner transfer process, which is basically a method of making a circuit board using a laser printer, photo paper, and a clothes iron. And then you etch it in some acid you can buy in an electronics store. And it worked out really well. That's a picture of the final board before we drilled it. And then we drilled it and soldered it.
Okay. So after the board was built and the sensors were put into the casings, the glove had to be constructed itself. We went with a glove that the material was thin, it was elastic, it could bend, it was durable, it was comfortable. And what we ended up doing is we stitched pockets, 2 pockets per finger, 1 for each sensor, with anti-static lens cleaning cloth. We just cut it, and then after we inserted the sensors, we stitched them down. And then here you have all the leads that lead to the circuit board. And the circuit board is attached to like a foam mat that we cut and put Velcro on, so it's adjustable per person. And then on top of the leads itself, kind of to fasten them down and create a mount for the Hydra, we used another foam mat and then a foam baseboard. Fortunately, we had to put the Hydra controllers directly on. What we wanted to do initially was deconstruct the Hydra controllers and put that circuit for position tracking on the glove itself. What we realized is that the buttons on the top of it are hard to bypass. A lot of people have tried to do that and have not been successful, so we just put it on top of it.
So this is the flowchart of our software. This all happens in Unity. because we basically report the values back using Arduino, and then we do our processing, software side, computer side, in order to make things simple, keep them together, basically. So basically what happens is the values are captured from our analog to digital converter pins, and then our values are linearized. Those are the equations that Baird showed you earlier. From there, the values are basically normalized. It's basically a process in which it compares calibration values from two poses of the hand, a closed position and an open position, and then it's able to normalize between the values 0 and 1 to get that fully, where 0 is fully closed and 1 is fully open. And then from there we calibrate those, we interpolate those values from our 0 and 1 floating point values to an angle which we apply to the hand. Now, if we need to calibrate those values because they're different for each hand, we have buttons that allow us to calibrate what those values are. And we will actually capture what those normalized values are, store them, and then when we normalize them here, we'll use those values again. This process is repeated about 60 times a second based on the frame rate of the simulation. So we used Unity. Unity is a little bit different than typical, C#, C++ programming, in that you place objects into a scene, but you have a hierarchy view here. These are all your game objects that are in the scene, and you can organize them into structures, drag and drop them, move them around, and those relationships determine how these objects behave. But the last thing to understand about it is that you can attach a script to any of these objects. For instance, I could put an object into this, a script into this table that makes it move or explode or anything that I want it to. That can be programmed in either C# or Java. And an interesting thing to note about it is that it is actually compiled in a native code. It is the fastest, they claim it is the fastest implementation of Java available.
So in order to get those models into Unity, you have to make them somewhat first. Now, we have the option to using off-the-shelf stuff, which we download, but that wouldn't make for a very good learning experience. So what we did was use Blender. It's open source 3D modeling software. It's the models that it generates import natively into Unity. It's well documented. There's a large community, and it's easy to find resources for it. From no knowledge, I was able to make this hand over the course of a week, and it's using a tutorial that I was able to find on YouTube. It's very user-friendly, easy to use, and some details about the hand model. It contains just over 1,000 vertices, about 2,000 edges, and about 1,000 faces, and it's UV mapped using a 1024 by 1024 resolution texture. And over here, you can see the UV mapping as well as the mesh over here. Slide, please. So, any product is going to cost money to develop, and here's ours. We have a breakdown of all of the different components that the team members bought, and on our own private tracking, we also have who bought what, so we get reimbursed evenly at the end of the semester. So this top section is who spent, individual components. Down here we have the lab provided supplies. And finally, taking up the majority of the cost is labor, $8,000, which we calculated based on what four people making $6,000 a year would make over the course of 4 months, 40 hours a week. And lastly, to note, this $460 is the total value of all the components that we spent putting into the project. So, next slide, please. And here's what we hope it would cost for mass production if we were to bring this forward. The top component is the Atmega 32E4, which is the microcontroller used in the Arduino Micro. Glove, pair, one for each hand. PCB/fabrication costs, bend sensors, got the 10 for each hand, so 20 total. Sewing costs, and the absolute positioning system. Now that's what we use the Hydra for in our prototype. Moving forward to production, we would probably want to use something that we create ourselves